In this lecture video, we will be discussing the E1 reaction mechanism, which is basically a stepwise mechanism in the elimination reaction, in which the first step that's going to happen will be the loss of the leaving group. So this is the first step going to happen, followed by the proton abstraction or the proton transfer, and that will be the second step. And below is the reaction mechanism of an E1 reaction. So let's say here we have a substrate connecting to a leaving group. In the E1 reaction mechanism, the first step that's going to happen would then be the loss of the leaving group, where the bond between the carbon and the leaving group is broken and the electron is going to the leaving group. And this is basically the rate determined steps of the E1 reaction. And once this step is accomplished, we will be producing a carbocation intermediate. So this is a carbocation intermediate. And once this carbocation intermediate is formed, the reagent would then behaving as a base. And the base will come in, pick up the hydrogen, one of the hydrogen, at the beta position. So here in this case right here, there are 3 beta carbon with hydrogen on them. And because they're symmetrical, it does not matter which beta hydrogen that we will pick up. So here in this case, we'll come in, pick up one of this beta hydrogen as a proton. The electron is then donated in to form the double bond with the carbocation. And the structure would then be the formation of the alkene. And the rate equation of this reaction is then equal to K multiplied by the concentration of the substrate. So the reaction is then dependent on the concentration of only the substrate. So this is why we call this the E1 reaction. And in addition to the 2 steps that we have seen above already, the loss of the leaving group and the proton transfer. So these 2 steps right here are the core steps. So this is the core step number 1, and this is the core step number 2. In addition to these 2 core steps right here, there can be another proton transfer at the beginning of the reaction, or another step that will also be possible would then be the carbocation rearrangement. Because we can see in the course of this reaction right here, we do generate a carbocation intermediate. And if this carbocation is not stable, it can be rearranged to produce a more stable carbocations. As for the initial proton transfer, if the leaving group is not a good leaving group without protonation, and if it have to be protonated in order for it to leave, then that's when we need to add acid to make sure we can proceed with this proton transfer. So this step right here will be needed if the leaving group is not a good leaving group. Can't leave if the leaving group can't leave on its own. And now let's discuss the effects of the substrate on the E1 reaction mechanism. So E1 is very sensitive to the structure of the substrate, in which the more substituted the substrate, the faster rate of this reaction. And we have seen that this is actually very similar to the trend that we have observed in the E2 reaction mechanism as well. So the more substituted the substrate, the faster the rate of the reaction. So the tertiary substrate will be the most reactive. And the explanation for this is due to having the more stable carbocation intermediate. Because we have observed already in the reaction mechanism, there is a carbocation that is formed. So the more stable the carbocation is, then the faster rate of the reaction. So the more stable substrate are able to produce the more stable carbocation intermediate. As for the residual selectivity of the E1 reaction, then the more stable And normally the more stable product would then be the more substituted alkene, or we also call that the Zajas product, would then be the major product of an E1 mechanism. For an example, give an example of this substrate right here reacting with concentrated sulfuric acid at 80 degrees Celsius. So here in this case right here, it will undergo an E1 reaction mechanism. And the product form will be as follows. This will be the major product. And in fact, the yield of this is 90%. And the other alkene that can also be produced would then be this following product. And this would then be the terminal alkene, and this is the minor products. And the percent yield of this reaction is about 10%. So here in this case right here, we have different beta hydrogen. These two beta hydrogen right here are similar, so removal of both of the hydrogens on these two carbon right here would produce the same alkene, whereas this beta hydrogen right here on this carbon would be uniquely different. And here in this case right here, the major products is the product where the base will come in and abstract the hydrogen from this beta hydrogen right here. And the explanation for this is as follows. This carbon right here is more electron rich compared to the other two carbon outside, because it is more substituted, and therefore it is more willing to donate the electron into this to form a double bond to stabilize the carbocations. And therefore the major product is normally the most stable alkene. As for the stereoselectivity of the E1 reaction mechanism, then the more stable, there's no stereochemistry control. However, the more stable stereoisomer is the major product. So the cis alkene or the more stable alkene, where the two bulky group on the different sides of the double bond would then be the major products. For an example, when we take this alcohol reacting with sulfuric acid and heat to do an E1 reaction mechanism. So here in this case right here, due to symmetry between the left side and the right side, we can pick up this hydrogen either from this side or the other side. Does not matter at all. So here in this case right here, the two products that we will produce will be as follow. Or the other product that can also get formed will be as follow. So this is basically the trans. Well, in this case right here, we would not be using the word cis or trans, and that is not relevant here in this case. But here in this case right here, these two bulky group right here are on the different sides of the double bond. So here in this case right here, this would then be the E product, and this would then be the major product because it is more stable. The other alkene product, where the two groups are on the same side of the double bond, this is less stable. So although it does form, it is formed as a much lower percentage, only 25% yield. So that's how the stereoselectivity work out in an E1 reaction mechanism. So basically, the major product would then be the more stable alkene. And carbocation may happen in the E1 reaction, and therefore we will be forming products from the carbocation rearrangement as well. For an example, here in this reaction right here, we have a secondary substrate, and here we're treating this with concentrated sulfuric acid and heat to do the E1 reaction mechanism. And we will then observe the following. The major product is as follows. So that is the major product. And the percent yield of this reaction right here is about 64%. And the other product that can also be formed would then be this other product here. And this product right here is also a product of the carbocation rearrangement as well. And this form at 32% yield based on experimental observation. And the other product that would be produced will be the product where it do not undergo carbocation rearrangement. So these two products right here are the product of carbocation rearrangement. And if we were to write the mechanism of this reaction, it would then be as follows. First, hydroxy group is not a good leaving group, so therefore it needs to be protonated first. So this is why that we are doing this reaction in concentrated sulfuric acid. So the hydroxy group will come in and pick up the proton from the sulfuric acid and become protonated first. Once it is protonated already, it can now become a good leaving group, so it leave on its own, producing this product. And this is a secondary carbocation, which is not the most stable types of carbocation that we have seen. So here in this case, it would then undergo carbocation rearrangement through methyl shift. With the methyl group from the nearby carbon come in and attack that. And now we are forming a tertiary carbocation, which is more stable. And in the next step, the base, in this case right here, the hydrogen sulfate, will then come in, pick up this beta hydrogen, and now the electron is donated in to form this alkene. So this is the most stable alkene, and therefore it is the major product. We can also form the other products. So here in this case right here, we can also form the other product where now the base do not, so this base right here will then come in and abstract the hydrogen in here. One of the hydrogen in here, donate the electron in, and that's how we are producing the product above here, the terminal alkene. And this product right here will then be the product without carbocation rearrangement, where at this step right here, we can simply have the base come in to pick up this hydrogen to donate the electron in and forming this product above here. So we'll form a mixture of both the rearrangement products and the product without the carbocation rearrangement. And again, the major product would then be the most stable alkene from the carbocation rearrangement mechanism. Let's now try a few examples right here. Let's predict the products of these various reactions. So now let's try this example number 23. So here in this case right here, when we take this reacted with ethanol and heat it, what would be the product? So here in this case right here, the bromine is a good leaving group. It does not need to be protonated, so it can leave on its own. So therefore, the first thing that we're going to produce will then be this carbocation rearrangement, this carbocation. And in this case right here, this carbocation do not need to be rearranged. So in the second step, so ethanol, it acting as a weak base, and that will then come in abstracting this hydrogen right here, because the removal of this hydrogen will then produce the most stable alkene that we can produce. And we want to write the mechanism that explains the formation of the most stable alkene. So this will then be our major product. And now let's try another example, number 24. So here in this case right here, we again taking this alcohol and reacting this with sulfuric acid. So what will be the products? So why don't we take a minute to work on this first before we go over the answer together. And now let's go over the answer. So here in this case right here, it will undergo the E1 reaction mechanism, and the product that we will be producing will be this product right here. And here in this case right here, we are basically forming the E alkene, or the product in which the two groups are on the different sides of the double bonds, and this would then be the major product. And as for number 5, the major product of this reaction would then be again, so in this case right here, it will undergo the E1 reaction mechanism. So the first step going to happen would then be the protonation, followed by the leaving of this hydroxy group, forming a carbocation right here, and followed by the proton transfer, where the base, the hydrogen sulfate, will act as a base to come in and pick up this hydrogen right here, and will be forming the double bond between these two carbons. So the major product of this reaction would then be as follows. So this is the alkene. And now let's try drawing a few of the reaction mechanism for the E1 reaction. So drawing mechanism of this type of reaction right here should be relatively easy. So let's go over one of an example. Let's do this example right here, number 27. So here in this case right here, we are providing you with the products, and we asking you to draw the mechanism that explains the formation of this product. So the first thing we should do here is to analyze the reactant and the products and figure out which carbon is which, so that will give us a good clue of what is going on in this reaction. So here in this case right here, we will then see, okay, so a double bond is formed between these two carbon right here. So this carbon, let's call this carbon is this carbon in here. And now right here we can see that because this carbon right here, so let's call this carbon A and carbon B. Carbon B on the reactant is not connected to a leaving group. So we will then see that first is going to leave first, this going to leave, and then there will be a carbocation rearrangement followed by the abstraction of this hydrogen in here to produce the double bond between the carbon A and the carbon B. And that would be the mechanism of this reaction. So the first step would then be the proton transfer. And now we need to keep the stereochemistry the same thing because nothing has happened to it yet. And once this is now protonated, it can leave as water. Notice how the carbon B, its stereocenter still have not been affected. And here in this case right here, we are producing a secondary carbocation. And we know that this is not the most stable types of carbocation. So here in this case right here, it would then follow by a carbocation rearrangement through a 1,2 hydride shelf. And the mechanism of this reaction is when we have this hydrogen from the back combine to attack this carbocation. And now this carbon B right here, it will no longer be a chiral center. It can now become a carbocation, which is achiral at this point. And on the next step, the base. So in this case right here, we can use hydrogen sulfate as a base, and that would then come in, pick up one of this hydrogen, so we can double bond. And again, I have to pick up this hydrogen right here in order for us to form the double bond between these two carbon. And the product of this reaction would then be this double bond. And that is the same product that we are supposed to write the reaction mechanism for. So mechanism of E1 reaction is relatively easy.